presentation little brief. So I will be just giving a representation of the thermonuclear functions with depleted tail via generalized special functions. This is just to explain how special functions are being used in uh, various applied areas like astrophysics. So here what this is a paper which is a joint paper with my collaborator Professor Hans J. Hobold, and this paper is published in Axioms in the last year 2021. So anybody can download the paper from the Axioms website, the journal Axioms website. So and what in this what I am going to do is just to give a closed form representation of the non-resonant thermonuclear functions in Maxwell, Boltzmann, and Salis cases. Already with these Maxwell, Boltzmann, and Salis cases were obtained in closed forms via generalized special functions. But main difference is that here we will be instead of using a summation series, we will be using a h function of two variables it in a single analytic solution. So that is the main advantage of this work. So we will be considering both the Maxwell, Boltzmann and the Salis cases, and it is done by using the double Mellin-Barnes technique. So that is the main advantage of this. I have used many terms which I will explain one by one. And I will also give a brief idea about the behavior of the generalizations which I have done here. Okay, I hope you all know that the energy produced in the sun, like stars, are due to the thermonuclear functions taking the thermonuclear fusion reaction taking place in the sun. It is the core where the nuclear fusion reaction takes place, and passing through the various zones, it will come as the energy to the earth and every part of the universe. So consider a nuclear fusion reaction where we consider a particle of type I and a particle of type J. Here we are just considering any two particles. In physics they may consider many physical or chemicals which are reacting, but here we will consider it as a particle of type I and particle of type J are colliding with each other to produce a particle of type P and a particle of type Q with some energy. So this can be symbolized like this. But when we consider the reaction rate is a probability. There is a reaction rate probability. That is why we call it as a reaction rate probability, and it is defined as in equation here. Sorry. Here this angle bracket says that it is a suitable average of the reaction cross section, which is given by the sigma and relative velocity of the particle. In this equation here, f of v represents the velocity distribution and sigma v represents the this reaction cross section. So usually it is assumed that the velocity distribution followed is Maxwell-Boltzmann by assuming that there is a thermodynamic equilibrium. So by assuming that, they assume that the velocity distribution followed is Maxwell-Boltzmann. So when Maxwell-Boltzmann distribution is substituted here in equation 2, what we are getting is here in equation 4. So here this sigma E, as I told, is here we consider a non-resonant thermonuclear reaction. So there is no resonance taking place during the reaction. So we will be considering an expression like this, where S of E is a slowly varying function of energy, which can be expressed in the form of a where the higher order terms are negligibly small. That is why we are omitting that. So we can replace, we can substitute these values in this reaction rate probability integral in equation 4, and why it is called the probability? It is called the probability that the two particles of type I and J confined to the unit volume will react with each other. So that is why this is called the reaction rate probability. Okay, so when you substitute these values here, we are going to get an equation in this form. So here, if we give a symbol substitution, the whole integral turns to be a simple integral, which is to be evaluated. But normal conventional techniques cannot be used to evaluate this integral. So we will be using an integral transform technique to solve this. So starting from the 1984, several papers were evolved solving that. So the technique is that we will consider which is to be evaluated this. So we will consider a general form of the integral. We call it as I1 for sake. This is the integral which is we call that since we are using the Maxwell-Boltzmann velocity. So we can call it as a Maxwell-Boltzmann this integral is called the reaction rate probability integral in the Maxwell-Boltzmann case. So if there is a cutoff in the high energy tail, then we will be taking a D, which is a cutoff value, and that in that case the integral will be this, and in the general case we can consider an integral like this, which is in equation number 12. And if there is a depletion, so here I am focusing on the depleted reaction rate. So if there is a depletion in the high energy tail, then this integral is to be considered, where the general form of the integral is given in equation 14. So usually when type of integrals, what they do is one exponential function has been taken as a summation, and then the remaining part can be solved by using the Mellin-Barnes technique, Mellin transform technique. So that is the way usually people usually this was if there is a screening in the high energy tail, then we can consider an integral in this form, which is equation 16. Now these integrals were all solved by Professor Mathai and Hobolt in their earlier papers of 1980. Starting from 1984 onwards, they had a good collaboration and had so many results on this. The reaction, they have obtained these results in terms of the H function and the special cases in G function. So this is already there in but what we are going to do is that instead of taking the summation, without taking the summation, we are going to solve this. We are not using any summation here. Instead, we will be using the double Mellin-Barnes technique by taking these two as different functions. So that is the main advantage of this method. So here, let us recall what is a double Mellin transform of the function f of x1, x2, or Mellin transform of two variables x1 and x2. So it can be written as mf of s1, s2. This transform variables s1 and s2. So here this is the expression for that. And once you take the Mellin transform, we will get the transformed equation we will get, and to retrieve the original function we have to take the inverse Mellin transform. So that is the technique. So the inverse Mellin transform in the double variable case is this one in equation 18. So for reference, you can go through the books for papers of Fox 1957 or High and Yakubovich on double Mellin Barnes. You can refer to this book. Okay, so we can consider the I3 which is given here. Now you apply the double Mellin transform here with the variable t and z. So that is the two variables which we are using here for taking the Mellin transform. This can also be done by using the Mellin convolution property. So in that case, we will be obtaining this in terms of the product of two functions. So that is also possible. In the in the papers of Mathai and Hobolt, they use the Mellin convolution technique. So that will be more easy when we can consider it as two functions, individual two functions, and take the Mellin transform of the individual functions, and then you take the product. So that is also possible. But here I have done all the thing together. I have done this in a single equation. I have done the Mellin transform. So that is the difference. So here I applied this integral and changing the order of integration because these functions are uniformly convergent. So we can interchange the integrals. Now you integrate, and using the gamma functions, the definition function, you can just write the gammas here, and this is also again a gamma function. So finally you will be getting here with these conditions. So these three conditions are there, and here you could see that there are functions with the single gamma functions S1 and gamma of S1 and gamma of S2, and a gamma function which has the elements with S1 and S2, the term containing S1 and S2. So this cannot be written in terms of a single variable h function. So we have to go for a double variable or h function. So h function of two variables. So taking the inverse Mellin transform, we are going to get in terms of h function. So I will just show you how this is written after explaining what is an h function in two variables, the definition of the h function in two variables. So this for non-negative integers m1, m2, m3, n1, n2, n2, p3, q1, q2, q3, we have this conditions. These are all real positives. These are complex numbers. We can have this. This is actually this expression is actually a similar version of the h function in one variable. It's having some more difference, a little bit difference is there. So let us see what it is. It is also a double Mellin-Barnes type integral. The ordinary h function in single variable is a single Mellin-Barnes type integral. Here there will be two variables, x and y are there, and how we will be writing this, let us see. Before that, we have to see what all these functions are. This is a double Mellin-Barnes where this h1 or h1 s1 s2, h2 s1 and h3 s2 are functions which are given here. h1 of s1 s2 is this. It's a product. Call it as a positive gammas. We can call it as positive gammas because the coefficients are positive. So we can call it as positive gammas with S1 and S2. So here it is a product of positive gammas in the numerator. Here there are these are the product of negative gammas in the denominator. These are the product of positive gammas in the denominator. Here the product of negative gammas in the numerator is missing. So there is no negative gammas in the numerator because we need only this type of an h function. So that is why we have considered this. So here there is no negative gammas in the numerator. So we will be taking this type of an h1, s1, s2. So what is m1? M1 in this we have written m1. M1 is the number of positive gammas in the numerator with s1 and s2 and with plus the number of negative gammas in the denominator of this. Okay. Now what is h2 of and what is here n1? N1 is nothing. N1 is not there. N1 is 0 because there is n1 is taken 0 because there is no negative gammas in the numerator. So that is why it is taken 0. Okay. So now in this function, this part there are we have m2. M2 is the number of positive gammas in the numerator plus the number of negative gammas in the denominator plus, and the n1 n2 is the number of negative gammas in the numerator plus number of positive gammas in the denominator. Okay. So sorry, I am talking about p1 and q1 and q1 and p1 and here q2 and p2, not the m1. M1 is the number of positive gammas in the numerator. Okay. And here q1 is the number of positive gammas in the numerator plus t gammas in the denominator. So that is q1. Okay. And p1 is the number of positive gammas in the number of negative gammas in the numerator plus number of positive gammas in the denominator. So p1. And here it is the same as that of an h function. Here it is number of m2 is the number of positive gammas in the numerator, n2 is the number of negative gammas in the numerator with one variable s1. And here q2 is the number of positive gammas in the numerator plus number of negative gammas in the denominator. So like in the same way it is m3 and n3. Okay. So we can see how it is written. So in this function we have one positive gamma because s1, the coefficient of s1 is positive and the coefficient of s2 is positive. So we have to consider only one positive gamma in the numerator. There is no terms in the denominator, so don't bother about that. So one positive gamma in the numerator. So that is why we have written 1 and no negative gamma. So it is Then again M2 is a number of positive, one positive S1 gamma and one negative one positive S2 gamma. So that is why 1 here. No negative gammas in the denominator. So that is why it is 0, all the 0. And P is the sum of the positive gammas in the numerator plus negative gammas in the denominator. That is also not there. So that is why it is 0, 1, 0, 1, 0, 1 like that. Okay. So and here it is nothing but the gammas which is written in this form. So if there are positive gammas, you can directly write that functions. The coefficients are directly written here. Gamma of it is gamma of bj plus beta j s1 plus bj s2. So here it's a coefficients. It's a constant one. This is the coefficient of s1. It's the coefficient of s2 like that. So here we can write it as minus. See, constant one is minus gamma by rho, and here is 1 by rho s1 coefficient of 1 by rho, and this is delta by rho, and here only gamma of s1. So the constant term is not there. So 0, 1, and here also 0, 1. So this is the simplest form. And this is convergent for all values of z because this p is greater than q in all the cases. So that is why. For more details on this h function of two variables, you can go to Srivastava's book or from Mathai and Saksena's book is their 1978 book. I will show the reference. Anyhow, so this way we can represent this in terms of a double two variable h function. Okay, so that is the advantage. Now, if we give a simple assumption, you can use if we consider that the delta by rho. See here we are considering one delta gamma by rho is an integer. Sorry, delta by rho is an integer. Then we can use multiplication formula for gamma functions here. Delta by rho is an integer. Then you use multiplication formula for gamma functions, and you will end up with an h function in two variables like this. Just for a mathematical curiosity, we are writing this expression. There is no other thing. And for special cases in physics, we have gamma is 1 plus nu and rho is 1 by 2. So we will be getting in physics, the equation will be this. Okay, so there is no summation arising in this expression. So that is the main advantage of this result. So usually in the beginning I told that in the reaction rate probability integral we have assumed there is a thermodynamic equilibrium, but in normal case it is not like that. We have to think about distributions which are non-equilibrium. There are situations which are non-equilibrium also. So if there is a non-equilibrium situation, then we have to think about other distribution, velocity distribution, which can be considered for the special cases also. So I will just move it in 5 minutes. I will wind up. So what we did is we changed the velocity distribution from Maxwell-Boltzmann to a new velocity distribution by using a mathematical model which is called the pathway model. A pathway model was introduced by Mathai in 2005. The model was actually derived as a model for matrix variate case, but scalar case is a special case there, and you could see the special cases also in this paper, and more special cases can be seen in the paper of Mathai and Hobold in 2007. So I can show the references also. In scalar case, it is a function which is moving among three different functional forms. One is generalized type 1 beta form, the other one is type 2 beta form, and generalized gamma form. Functionally, they have no difference between the time. There is no much difference, but behavior is entirely different for a type 1 and a type 2 beta distributions. One is a cutoff case, the other one is a general case. So this one is a cutoff type integral because q is less than 1, and here it is a general case which goes from 0 to infinity. So type 2 beta case. This is a type 2 beta case, this is type 1 beta case, and this is gamma case. So by using this method, what we are going to do is we are just obtaining a new velocity distribution, and we replace this Maxwell-Boltzmann by using this, and then we replace this distribution with the reaction rate. We replace the Maxwell-Boltzmann with this, and we will get the equation in equation 33. So this has been this can be simplified in this form, and the integral to be evaluated this. And the evaluation of this in terms of h function of one variable and g function of one variable has been given in the papers of myself with Cobalt in 2008 and 2011. You could see that. And but here also what we have done is we have used that depleted case. We have considered the depleted case and solved it for solved in terms of this two variable h function. So I am not going to explain that because it is a similar procedure we can do this. So these two are the major results which we have obtained in that paper with the physical interpretations of that. So I am just dropping here because it's already time. So these are the results for that two variable h function. And note that as here is alpha tends to 1, we can retrieve the results for the Maxwell-Boltzmann case. So that's the result. And anybody can download this paper from that site. So thank you very much for listening. I think it's a time, and this is the behavior of this pathway density function which with the Maxwell-Boltzmann. We have plotted this for various values of alpha. You can see this. Okay, anyhow, we have made an attempt to change the velocity distribution. Pathway energy can cover the unstable and chaotic situations. And also as the limiting case, we will retrieve the Maxwell-Boltzmann case. And also if we change a small values for alpha, we will get a drastic change for the nuclear reaction rates. So that is the advantage of this. So thank you very much for your patient listening. And these are reference. And for those who are new to this subject, let me give, these are special cases of pathway model, super statistics and Salis statistics, special cases of pathway models. You can refer to this Salis statistics. For Salis case, you could refer to the book by Salis and Gell-Mann of 2004, non-extensive statistical mechanics or non-extensive entropy. You can consider. And this is the book which I was mentioning, double Mellin Barnes type integrals. And this is the paper, Matai 2005 is the paper where pathway model was introduced. And these are the series of papers of Matai and Hobold where the standard reaction rate probability integrals were given. And here you could see the techniques in the standard cases. So this is the scale for scalar case. You could refer to the pathway model, refer to this paper for the scalar case of the pathway model. And where is my? Yeah, these are the papers where you could see the extended reaction rates and their applications are published in Astroparticle Physics and Journal of Plasma Physics. So these are the papers, and this is also a paper where we are giving the series representations. Okay, anyhow, thank you very much.